Use the constant, constant multiple, and power rules for monomials. Alright, so just a quick review about derivatives. So to find the slope of a point on a curved line, we first need to find the slope of the line tangent to that point, and this process is known as the derivative. Now, using the derivative, we can find an equation that allows us to calculate the slope of any point on that particular curved line. But since it only allows us to find the slope at any point on that particular curved line, this particular equation will only work for that curve. And in order to find this equation, we will use the limit definition of a derivative. F prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And now this is the only way we have at the moment to calculate the derivative algebraically, is this particular limit, which is not so friendly and usually requires a boat ton of algebra. So today we're going to be learning a bunch of rules that help us take the derivative much quicker and will allow us to avoid this boat ton of algebra. But before we can do that, we need to go over some derivative notation. So just like notation was important with limits, notation is also going to be important with derivatives, just in a slightly different way. So let's remember, derivatives are all about change, because derivatives represent slopes, and slopes represent rate of change. So these derivatives, they show us how fast something is changing at a specific point, i.e. the instantaneous rate of change. So let's do a quick review of how we actually find the instantaneous rate of change. Well, first we need to start with the average rate of change, and we need to find the slope of that particular secant line, which is our normal slope formula, y2 minus y1 over x2 minus x1. If we wanted to, which we do, we can rewrite this as being delta y over delta x, which means the change in y over the change in x. And then in a previous video we had derived f of x plus h minus f of x all over h from delta y over delta x. Then once we found the average rate of change, we could go ahead and find our instantaneous rate of change. And we found that by taking the limit of the average rate of change, because that is the process that turns our secant line into a tangent line. And since we know the average rate of change is equal to delta y over delta x, we can really just set this equal to the limit as h approaches 0 of delta y over delta x, which we can then rewrite one more time to be the limit as h approaches 0 of f of x plus delta, the limit as h approaches 0 of f of x plus h minus f of x all over h. So now we have multiple forms. We talked about many different formulas or way of writing average rate of change or instantaneous rate of change. And to understand the derivative notation, we need to do that one more time. So to do that, we need to come back and we need to review what h is. Remember, h represents the change in x, the distance between x sub 2 and x sub 1. So in order to rewrite our formula, we can just rewrite h as being delta x, and h as being delta x, which means we'll have the limit as x plus delta x minus f of x all over delta x, representing the average rate of change. Now, how does that affect the instantaneous rate of change? Well, we'll just change all the h's to be the change in x, because again, that's what h is, giving us the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. And now we're going to be moving forward with this particular notation to help us understand where the derivative notation comes from. But before we do that, one final thing. Remember, since the intended height, since the limit will never actually equal the actual height, we know that delta x can't be 0, also because you can't divide a fraction by 0. So again, just a reminder about that. Now, while we know that delta x can't be 0, as we previously said, we want to make delta x as small as possible. We want to make it infinitesimally small. Remember going back to the whole epsilon delta proof. So what we do in math is we can say, okay, so if we want delta x to get as small as possible, let's call this infinitely small number, let's just call it delta x. So that means we can come in here, we can take the limit as delta x approaches 0. So again, as delta x gets smaller and smaller and smaller and smaller, we will call this incredibly small value that's so close to 0 dx. And then we can do a similar thing. We know that we want delta y to be as small as possible. Again, epsilon delta. And when we get this delta y to be as small as possible, we will call it dy. So again, if we look at the limit, and we want to get delta y to be so infinitesimally small, that incredibly small number is going to be delta y. And this is where one of our notations comes from. Because if we take a previous derivative notation, the limit as delta x approaches 0 of delta y over delta x, we know that the limit of delta y is going to become dy, and the limit of delta x is going to become dx, giving us our first derivative notation. Now, as we mentioned in previous videos, we also already have the derivative notation f prime of x. So now we have two derivative notations, dy over dx, which is referred to as the Leibniz notation. This is the notation developed by the mathematician Leibniz. Whereas f prime of x is a Lagrange notation developed by the mathematician Lagrange. Now, these two names are not important. You do not need to know any of these things. But what you do need to know is that dy over dx and f prime of x both represent the derivative. So with that being said, let's dive into some more derivative notation. Alright, so we already said that dy over dx represents the derivative. But to go a little bit more general, because we're not always going to be using the variables x and y, we could write this as being d of the output over d in the input. Because remember, y represents the output and x represents the input. Another way we can define this that might be helpful in certain situations is saying that instead of output, we say it's the function. And instead of input, we say it's the variable. So again, the derivative is d of the function over d of the variable. Alright, so now we're going to look at some derivatives as a function. So for example, we have already said that f prime of x represents the derivative. And we said that we could rewrite this notation as being dy over dx, because f of x is the same thing as y. Or if we wanted to keep the f, you might also see df over dx. And then rarely, some folks like to bring the f of x with it, so you might even see df of x over dx. So again, all four of these notations represent finding the derivative of the function f. Now, if we change our function to be g, or if we change our function to be s, we're going to just change certain aspects of our notation. So g prime of x can be rewritten as dg over dx, d of the function over d of the variable. And again, rarely, but sometimes you'll see this, d of g of x over d of x. Again, some people like to bring the x. Moving on to s of t. So not only do we change the function name here, we also change the variable, which means the derivative will now be ds over dt, or rarely ds of t over dt. And now all of this function notation is talking about the general formula for slope. So again, these different derivatives will come up with that formula that will allow us to find slope at any point that we want on a function. But what if we just want to find the derivative at a specific point? Well, that's where this next notation comes in. So again, these notations will tell us the slope of a particular point. So the notation is going to change a little bit. So for example, instead of having f prime of a variable, we're now going to have f prime of an input, meaning a. So f prime of a, if we want to rewrite that in different notation, that would be dy over dx, and then we put this big this big vertical bar here, and then down at the bottom we put whatever our input value is, in this case x equals a. Now if we didn't want to use y, we wanted to use f. Another common one is df over dx, vertical bar, and then down below x equals the input value. So again, these are all different notations that you might come across. Some of them are derivatives as a function or the generalized formula, and others want you to find the derivative at a specific point. Now, depending on how the notation is written is going to tell you certain things about the derivative. What do I mean by that? Well, for example, if we have d over dx or d dx of f of x versus df over dx, what is the difference between these two notations? And there is a significant difference. D dx of f of x means that the derivative needs to be taken, whereas df over dx means that the derivative has already been taken. One's a before, and one's an after. You can also think of d dx of f of x as the verb, because you need to take the derivative, and then df over dx is the derivative, so that is more of the noun. So again, lots of notation here for derivatives, lots of different types of notations, different applications of it, but fortunately when we actually go ahead and evaluate derivatives, it will be less notation than with limits. Speaking of which, let's take a look. So next up, we're going to talk about our rules for taking derivatives of constants, variables, and powers. So first off is the derivative of a constant formula. Now these formulas are great because these formulas are generalizations that come from the limit definition of the derivative. So these are really more like shortcuts, meaning we will not need to use the limit anymore to find the derivative. Praise the math gods. So d over dx of a constant c is just going to be 0. So the derivative of any constant will always be 0. Now, why is that? Well, let's take a look at a graph. And if we remember, constant functions are graphs of horizontal lines. So here's a horizontal line we'll call y equals c. And let's remember what the derivative is asking. The derivative is asking us to find the slope of the tangent line. Well, if our tangent line is horizontal, that means the slope everywhere on this tangent line is going to be 0. So that's why the derivative of any constant will be 0. So let's go ahead and take a look at some examples. First off, let's take a look at the derivative of 7. So now since 7 is a constant, we know the derivative of 7 is just going to be 0. Boom! Best calculus problem ever. Alright, next up, we're going to take a look at the derivative of pi. Now this one often confuses people because pi is special, meaning that we do have a Greek letter that represents a number. So sometimes people like to think pi is a variable, but it's not. Again, pi represents a specific number, and a specific number is a constant, so that means the derivative of pi is also 0. And then finally, the same is true for the derivative of our e function. Again, let's remember that our e function is approximately 2.1. And again, it does just represent a constant, so therefore the derivative of e is also 0. Boom! Derivative of a constant. Best math problems ever. Moving on, we need to find the derivative of a variable. So we're going to let a be any real number. So we're going to take the derivative of just the variable x, and the derivative of variable x is just going to be 1. Now why is the derivative of x just 1? Well, let's take a look at a graph. Alright, so if we were to graph the function y equals x, we would have this particular function here, y equals x. Well, let's remember that y equals x is a linear line, which means it is in the form y equals mx plus b. And we can see here that our slope for the function x is going to be 1, and b is going to be 0. again telling us the slope everywhere will be 1. Hence, the derivative of x is 1, because that's what the slope will always be. Well, then we can go ahead and we can kind of look to expand this, and we can take the derivative of some coefficient times x, such as ax. So let's go ahead and let's look at the graph of ax. So this particular graph will be y equals ax, but again, this is a linear function, and that's going to be written in the form of mx plus b. So we can see from our particular line here that our slope is going to be a, and our y-intercept will be b, but again, that tells us that our slope everywhere will be a. So therefore, the derivative of ax will just be a, or the derivative of a coefficient times a variable is just the coefficient. So let's take a look at some examples. First up, we're going to take the derivative of x, and we already know the derivative of x is 1. Next up, we're going to take a look at the derivative of y, but here's something that has changed. Notice how we're taking the derivative of y with respect to the variable y. So in this case, y is the input, and we know that because y is in the variable spot of our derivative. And we know the derivative of a variable is just 1. Boom, done. All right, moving on, we're going to find the derivative of 7y. Again, y is the variable, since the y is in the variable spot of our derivative notation. And using the formula up above, we know the derivative of 7y is just going to be 7. And then our last example, we want to find ddb of 42b. And again, notice b is the variable here. And again, we have a coefficient times a variable, and based on our formula, we know the derivative of 42b is just going to be 42. Woo! Derivative of a variable. And last but not least, we have the power rule. And this is probably one of the rules you are going to use the most in this class. Power rule is everywhere. So here we're going to let a and n be any real number. And we want to find the derivative, d over dx, of x to the nth power. Well, what we're going to do is we're going to take the exponent n, and we're going to move it to the coefficient, and then we're going to subtract 1 from the exponent. And that's going to give us n times x raised to the n minus 1. In the previous video we did talk about this. We had seen when we took the derivative of a quadratic function that we got a linear function. So whenever we take the derivative of a polynomial, we're going to go down by a degree, hence n minus 1. Now we can expand on this particular power rule by taking the derivative of a variable raised to some power with a coefficient of a. So we're going to do the same thing here. The derivative of ax to the nth power, we're going to multiply the n, and we're going to move it to the front, multiply it to the a, and then we're going to subtract 1. And that's going to give us n times a times x to the n minus 1 power. So let's go ahead and look at some examples. Our first example is going to be taking the derivative of x cubed. So, based on the formula, we said we're going to take the exponent, we're going to multiply it to the coefficient and subtract 1. So this will give us 3x to the 3 minus 1, or 3x squared, as the derivative. Next up, we're going to take a look at the derivative of x to the 5th. Again, we'll take the exponent, we'll multiply it to the coefficient, giving us 5x. Then we will subtract 1 from the exponent, 5 minus 1, which gives us 5x to the 4th power as the derivative. Next up, derivative of 2x squared. Same process. Take the 2, multiply it by 2. That's going to give us 4 times x raised to the 2 minus 1, because we have to subtract a power. This is going to end up being 4x to the 4x to the 1st, or just 4x. And last, and certainly least, is the derivative of 4 times x to the 6th power. So, 6 times 4 minus 1. And where's that extra writing coming from? Ghost. And this is going to leave us with 24x to the 6 minus 1, or 24x to the 5th as the derivative. All right, so now that we have these three derivative rules, let's go ahead and let's apply them. So we're going to find the derivatives of the following function. So for the first example, we have 6x cubed. And for this one, we can see that we have an x to the third power, which means we'll want to use the product rule. So we'll take the 3, we'll multiply it to the 6, subtract 1 from the exponent, and that's going to give us 18x squared as our derivative. For number 2, we have negative 4x, so this is the derivative of a variable that has a coefficient. And we know the derivative of a variable that has a coefficient is just going to be the coefficient. So the derivative of negative 4x is just negative 4. And then for number 3, we have 2 raised to the x power, so folks might think, oh, this is the power rule. So just take the 8, we'll multiply it by 2 to subtract 1 and get 16 raised to the 7th. And trap! That is not what we do. Sometimes students don't read the people don't read the question carefully enough, there we go, and they see an exponent and they automatically think power. But the power rule only applies if the denominator is, if the base is a variable, which it's not. And 2 to the 8th is just a number, a really large number, but it's just a number. It is just a constant, so therefore the derivative, if I had the right marker tip, the derivative is 0. And there you have it, using the derivative of a constant, the derivative of a variable, and the derivative of a power rules. Alright, so there's one final rule we need to go over that's going to help us when we are finding derivatives of all sorts of equations and expressions, and that is factoring a constant from a derivative. So we're going to let c be any real number, and we want to take the derivative of c times f of x. So if c is a number that can be factored out of f of x, what this particular rule says is that we can then factor it out of the derivative. So d dx of c f of x is going to be c times d df of f of x, and then we can take the derivative of f and end up with c times f prime of x. And then we can look at an example. So here, if f prime of 4 equals 6, and g of x is equal to 2 times f of x, what is g prime of 4? So as we can see here, we're looking for the derivative, so we can go ahead and start. So first, we're going to have to take the derivative of g of x. But as we can see here, g of x is equal to 2 times f of x. So we can substitute that in, so d dx of 2 times f of x. 2 is a real number, and it's being multiplied times f of x. That means we can factor it out to give us 2 d dx of f of x. And we know that d dx of f of x is going to be f prime. So we get 2f prime of x. All right, so what did we just find out? Well, we found out that g prime of x is going to be 2f prime of x. And we're going to figure out what the derivative is when x is 4, so we can substitute that in. G prime of 4 is going to be 2 times f prime of 4. And from our example, we're told that f prime of 4 is 6. So therefore, g prime of 4 is going to be 2 times 6, or it gives us an answer of 12. All right, folks, that is it. That is using the constant multiple, and the power rule for monomials.